Hi everyone, my name is Omid Mohseni and I'm a PhD candidate at Laughable Locomotion Lab, and today I will be presenting the latest results I got from my current work entitled like the muscle recruitment in response to upper body perturbations during walking. So what we did in this study was that with a collaboration with TU Delft, Professor Heike Valerie, we conducted walking experiments, and in that we asked subjects to walk on a straight line while they were wearing a backpack. And this backpack has a control moment gyroscope embedded in it. And what it can do is just it can exert torques on your upper body. So this already makes it a huge difference with regard to other works, because when it comes down to perturbation and analyzing perturbations on the upper body or in other segments, there are pushes or like surface translations. But now we can with this device have a torque on the upper body in terms of like a moment. And here on the right, you can also see some snapshots of the experiments when there is like a perturbation coming at two different instances, right? You could see. And maybe one thing to note already is that we targeted the frontal plane perturbations, and we exert around like 40 Newton meter on the upper body. But just so you know, because this system is underactuated, once you apply torque in the desired plane that you want, it also gives you undesired torques in the other plane. So 40 Newton meters in the frontal plane, and we got like 5 to 10 Newton meters in the other planes, in the sagittal and also the horizontal plane. So just so you know. And what we did was that, of course, we measured different things. We had the ground reaction force, we had cameras, we had like the EMG and the GRF. And what I will be focusing on today is only the EMG analysis, right? I will be happily discussing more of this stuff with you later on, but for now, let's stick to the EMG. And I will talk about two different things in EMG, the magnitude and the timing of that. Of course, we can all later talk about the recovery schemes. And we had also 4 different perturbation scenarios, 2 different timings, touchdown of the right, mid-stance of the right leg, and also the touchdown of the left leg, plus 2 different directions, ipsilateral and contralateral. So let's jump into the results. And first, let's talk about the magnitude of the EMG. So what you see here in this graph on the left, you see every point dot that you see here is like the relative mean absolute values of the EMG of the perturbed trials with respect to the control trials, right? So the red represents the right leg, the blue represents the left leg, and different shades of red and different shades of blue shows the different perturbation cases that we have, right? So quick look at the whole graph on the left, for instance, it shows you, if you look at the distribution of the graph, there is a tendency towards the proximal muscles. And as you can see, or maybe let's have a better overview of the results on the right. So you can, this is like the combined results of what you see on the left, so this is better to interpret. So you can see already that the biarticular muscles like rectus femoris and hamstrings are most responsive to this yaw perturbation. And after that, you can see the tensor fasciae latae, the TFL, it also is very significant. Of course, the TFL might be expected because this is one of the muscles that work in the frontal plane already, and it's like a hip abductor, so its function is to work in the frontal plane, but we are also seeing a contribution from the biarticular muscles. And maybe one thing to note already is that we performed like the same type of experiment, or a similar one, in 2019, where it was a standing perturbation, and the perturbation were in the frontal plane, in the sagittal plane. And what we observed in there was that also the biarticular muscles are the most responsive to this type of perturbation. We are seeing more or less the same thing also in here. So this is what I want to show you regarding which muscles are working more when there is this type of perturbation coming to recover from it. And now I want to talk a little bit about the timing of the activations. So here you can see 2 different graphs. I'm only focusing on 2 of the perturbation scenarios. I'm not going through all of the 4. And again, the right leg is shown with red, the left leg is shown with blue, and which in these horizontal lines that you see here are the increased muscle activations of the perturbed trials with respect to the control trials, right? And there are 2 things I wanted to point out here. If you quickly compare the left to the right, you can see on the right the duration of the increased muscle activations is longer than in the left, which shows that when the perturbation is coming towards a non-dominant leg, you need more muscle work. And the second thing I want to discuss and I want to point out is that when I was looking at my data, I had one hypothesis in mind. And the hypothesis comes from the paper of Horak, I think around 1998, which he performed a perturbation study, but the people were standing and there was like a surface translation. And what he observed was that when there is a perturbation translation, there is an activity, first starting in the ankle, then the knee, and then the hip. So there was a sequence of muscle activation. So I was hypothesizing that maybe the same thing applies here. So when I have the perturbation source in the upper trunk, then there will be the proximal muscles activating first all the way through the distal muscle, but it was not true. If you look at the first graph, for instance, you can see the tibialis, the lowest bar graph, it's activating sooner than the other ones, which clearly showed that you cannot expect that there is a proximal to distal muscle activation. Literally, your body uses all the muscles at its disposal if necessary to recover from the perturbation. So, yeah, to sum it up, I just wanted to give you like 4 key messages. The biarticular muscles, although they are functioning way more for the balance in the sagittal plane, they also work in the response more in the frontal plane. The TFL, the tensor fascialis latae, which is like a hip abductor, works also, is more significant. Of course, we also saw that the gluteus maximus and also the vastus lateralis in the previous pictures were also significant, but these were the 3 main contributors to perturbation recovery. And also, the 2 other key points, there is no distinct sequence of proximal to distal muscle activation, so you cannot expect that. And the last one is that when the perturbation is coming towards the leg that you're not dominant, probably you will need more time and more muscle work to recover from it. Yep, and I will be happy to discuss with you about the results and also the recovery strategies. There was not time to discuss or show all the results here, but I will be happy to discuss with you afterwards.
Really quick question, was the dominant leg your naturally dominant leg or the leg that was supporting most of the weight?
So we did a questionnaire before doing the experiments, and we checked for the limb dominancy. Okay. All the subjects had the right leg dominancy, limb dominancy, and we made sure that all of them stepped on the first platform with the dominant leg. So all of them are comparable. And I already excluded some of the subjects which were like having a different limb dominancy. Yep.
How sure are you that you're actually picking up activity of the TFL? Because I think that's very hard to measure with the EMG now.
Actually, it was. I was not involved in the recording of the data, but actually I had to throw 1 or 2 subjects just because the TFL was not measured at all. So it was actually quite hard for them to measure it as well.